from last time, we talk about function of two variables, right? And then we have fxy. This is the notation for function of two variables. And then I gave you an introduction that what are we going to learn is we're trying to extend the idea of limit, differentiation, and integration into two dimensions, right? Before we have limit fx where x go to a. This is what you learn from Cal 1. So we're gonna extend the idea to limit fxy where xy go to a point AB. So this is going to be interesting that how you extend the idea of limit. And then after that, before you have differentiation, which is f prime x, you have the formula that you can use the power rule, the chain rule, anything. Well, we're gonna look at differentiation in two dimensions. So the notation gonna be diff f with respect to x or diff f with respect to y. So you have to fix which variable that you are going to differentiate with respect to. And then after that, in one dimension, you used to have integration. And then in chapter 5, like next month. So once we complete differentiation, we're gonna go to integration, which is going to give you how to integrate fxy on the domain, the rectangle domain and general domain in two dimensions, which is going to be the most important one because you need to carry it to use it in other courses. So that is the idea that we're gonna learn in the next 2 months, I think. And then after that, we're gonna wrap up the course with differential equations. Okay, well, I keep talking because I want more people. And then now we have 25 students, which is good. Okay, we're gonna start talking about the very first concept, limits. So let's talk about limits. So in two dimension, as I told you last time, that when we learn limit in one dimension, so you're gonna have a point A, right? And then if you remember from calculus 1, when you want to compute limit fx where x go to a, so you used to have left hand limit and right hand limit. You used to say that you're gonna compute left hand limit here, and well, that means the notation is going to be limit when x go to a from the left fx, right? And then you have the right hand limit, which is going to be the case that x approach a from the right, and that is going to be limit fx where x go to a, and then I say a plus here. That means a from the right, and then you can check if they are equal to each other. If they are equal to each other, so that means limit exists, right? And this is equal to that number L. Well, that is the theory from Cal 1 for left hand and right hand limit. But as I told you last time, this is not easy for two dimension, because once you have the point A, B here, you will have so many lines that you can approach AB. So you can approach AB from any line you want. It is not going to be just left hand and right hand, because you can have any line as long as they approach AB. Well, we're gonna say that should be the case that we're gonna consider as a one case of limit two. So how do I adjust the extension into dimension? So that is the idea we're gonna talk about today. So first of all, we're gonna look at some theorem first. Well, because in Cal 1, when we compute limit, we used to say that we can plug in the number into the function because of the continuous thing. So in Cal 1, we used to say that if you have limit x squared plus 1, for example, x go to 1, you used to say that, hey, the easy way to do this thing is just you can think that x squared plus 1 is a continuous function, right? and then you say that you're going to plug in 1. So this is just 1 square plus 1 and 2. Well, this is what you did in Cal 1. And we like that. This is a very good concept. This is a simple one that, hey, we're trying to copy this thing to 2 dimension. So can we do that? So the answer is yes. So you can look at the one that I am going to highlight in light blue now. So as in a single variable cases, we have, well, if you have limit of constant, it's still constant. No matter what x, y go to a, b, it's still constant, right? And then if you have limit of x, well, you can treat it as you plug in x equal to a. So when x, y go to a, b, if you feel like you want to compute limit of x, well, just plug in a. Well, this is the same thing with idea of 1 dimension. You just ignore y, right? Because there is no y in your function now. So that means you just plug in x equal to a, and that is your limit. When you see limit y, x, y go to a, b, you just plug in b to y. Well, this is the first 3 conditions that you can use for sure. Well, fine. And then also you have a lot of theorems from this slide. So if you have limit fxy equal to L, limit gxy equal to M, well, the theorem that the limit theorem that you are so familiar from Cal 1, they are still okay for 2 dimension. So that means when you do the limit of summation, this is going to be just summation of limit. So, well, also difference, well, you have limit of f minus y, f minus g. This is equal to L minus M as well. And you can see here, if you have a constant multiplied with the function, you can pull out the constant outside the limit, right? And when you have the product, you can just break up into the limit of f times limit of g. And then when you have the quotient, so you can do like L over M like this. And then when you have the power, you can just take the power out, compute limit first, and then raise to the n power after. So you can see that, well, from the point of view here, you can see that the algebra that we have from 1 dimension, it still works in 2 dimensions. So you still can use limit of summation equal to summation of limit of product equal to product of limits of f to the n equal to compute limit first, and then you raise to the n. So that would make the world easier because you can compute everything easy by using these limit theorems. So I will show you some examples here. Example 3. Well, we're gonna calculate the following limits. So these 2 are easy. So let's start from 3.1. So we have limit 10xy minus 2y squared over x squared plus y squared, where xy goes to 1, comma, -1. So as in Cal 1, so you can just trying to plug in the number into the function first. If you get the real number, that's it, you're done. So I'm trying to, well, when I see this limit, I'm trying to plug in 10. Well, I plug in x equal to 1, y equal to -1, minus 2, y equal to -1, right? And then x equal to 1, y equal to -1. This is similar thing as in Cal 1, but you just do, you replace x equal to 1 here, and then you replace y equal to -1 here. And then you just try to compute. If your answer at the end, you get a real number, you're good to go, you're done. So let's see here, I'm gonna have, let me compute this thing. So you get -10, and then -2, and then over 2. Yeah, good. Someone help me in the chat already. -6. Thank you, Mr. Well, Purohit, right? Yeah. Well, if you want to help me computation, so you can to compute something, you can just tell me the answer in the chat. All right, so we're gonna have -6 here as my answer. So, well, the conclusion is yes, limit of 10xy minus 2y squared over x y set. Xy go to -1 and -1, right? This is going to be -6. Let me set up something. Okay, that is question 3.1. Sounds good? Well, this is the easy case, but the case that you're gonna have a problem is the case that you're gonna face if you face 0/0, right? This is going to be the case that you need to do something, right? In count 1, when you face 0/0, well, Ajahn Thirapong said that you could do the factoring, or you could do the conjugation, or even better, you can do the L'Hopital rule. That is from count 1, right? Well, you have so many choice when you see 0/0. Well, 0/0 is the thing that is called indeterminate form, right? From count 1. Well, it still can be any number. So the technique that we're gonna solve 0/0, you can do factoring or conjugation or L'Hopital rule or something else. But well, let's see what could we do for 2 dimensions. So let's say I am going to do question 3.2. All right, 3.2 here, I'm gonna plug in number 2 and 2 first to see if it's good or not. So I'm gonna plug in that, so I get 2 square minus 4, and then 2 times 2, and then minus 2 times 2. Well, you can see clearly that this is going to be 0/0. So it will not work if you use the, just direct standard method. So, well, you have to do something. Well, factoring still work in 2 dimension, because factoring, you just need to simplify your function. Conjugation still work in 2 dimension because it's just the simplified thing. But for L'Hopital rule, there's no L'Hopital rule for 2 dimension. So you're gonna lose this thing because we do not have L'Hopital rule for 2 dimension. So you cannot just differentiate the top one, differentiate the bottom one. It will not work. So the best way to do when you face 0/0, you just need to simplify by factoring or conjugation. So for this question, well, let's do that. Let's factor it out. Well, I just copy the question first. Here, what I'm gonna do is I'm gonna factor the top one to be y minus 2 and y plus 2. Well, I told you, if you have a hard time to factoring, you need to review yourself, because well, when you learn limit, sometimes you need to factor something. So at least for quadratic equation, you need to factor for sure. So I do expect you to factor something. On the denominator here, we can pull out x, and then you have y minus 2, right? And then here you're gonna cancel out y minus 2, and that will leave you limit x, y go to 2, and then y plus 2 over x, and this is going to be 2 plus 2 over 2, which is 2, right? So many 2's, right? Okay, good. So we get the answer for this question, which is 2. I have a question in the chat. So our friend said that how to differentiate if that both x and y present. So as I told you that when I say there's no L'Hopital rule here, that means you cannot use the L'Hopital rule in 2 dimension. Well, you cannot use the L'Hopital rules for 2 dimension limit. Well, there's no theory about L'Hopital rule in 2 dimension. When the French mathematician named L'Hopital, he developed the theory only in one dimension. So in two dimension, you cannot use the L'Hopital rule. So forget about it. You cannot differentiate top one and bottom one. Okay, that's good. All right, next, let's do example 4. So I'm going to show you how to compute something. Let's just spice it up a little bit. So example 4. So let's look at this one. So now, well, you can see my technique. If you already forgot everything, so every time when you compute limit, so you're trying to plug in the number into the function first to see if it's just easy to compute or not. So if I try to plug in number 4 and 5, so I'm going to get 4 plus 5 minus 3 over 4 plus 5 minus 9. You can see, hey, this is 0 over 0 again. Well, and most of the time, you're going to get 0 over 0 because, well, if it is easy, I will not, give you a repeat question to compute and it is all easy. No. So the case that is going to be the hard one is 0 over 0. And, well, if I ask you to compute limit, most of the time, it's going to end up with 0 over 0. And then you have to use something else to solve it, not just plug in number. Here we are going to, we already see that this is 0 over 0, right? So, well, you can try to factoring or use a conjugation. Some students are good in factoring, so you can factor out. But, well, if you feel like you are not good at factoring, so you can just try conjugation first. Well, what I'm going to do is I'm going to just say that, well, this is the question, right? Every time when you see this thing, the square root thing minus number here, if you remember the technique from Cal 1, we're going to multiply something called conjugation. Well, I multiply x minus y plus 3, both on the top and on the bottom. So the thing that I multiply here is just number 1, right? Because it just, they cancel out to be 1. So this term, this is just number 1. So it's okay to multiply the same thing here. And the reason why I multiply this, because I know that the conjugation, right? So the conjugate of square root a plus b, this is square root a minus b. So the reason why we multiply this thing, because at the end, when you use the conjugation properly, it's gonna, group it up, and the form is going to be a lot easier. So here, what I'm gonna do is I am going to multiply the top one, and then you can see if I multiply the top one, so you're gonna get x plus y minus 9, because you have square root x plus y minus 3 and square root x plus y plus 3. So, well, it's like you have a minus b and a plus b, right? And then you just multiply, so you get a squared minus b squared. And then on the denominator, just keep it like that, because you expect something to cancel out. All right. And then now the next step, you can see, wow, this is good because this thing cancel out. And then now at the last step, you can just plug in number. All right, this is going to be 1 over 6 as you answer. Simple like that. So from the first minute of the class up to this point, so we already know how to compute limit by just, trying to plug in number first. And then if you face 0 over 0, try factoring and conjugate first and see if it works or not. Sounds good? Any questions so far? All right, good. So now we are going to show you another technique for 2 dimensions. In 2 dimensions, because the behavior of what I just told you before, that the limit can approach the point AB from any line here. We're gonna have 2 more techniques for you to compute limits. Because of this pattern, so let's see. So I'm gonna go back to that page. What are the difference compared to 1 variable case? Well, I am going to draw a picture here again. In one dimension, so I keep saying this thing. Well, you have A here, and then you have limit only left hand and right hand. But in two dimension, the point A, B here, and then you can have any line, any line, any line, any line, any line you want, but just approach it A, B here. Remark number one. So if limit of the function f where x, y go to a, b exists, well, if you know that the limit exists and it is equal to L, then the function fxy gonna go to L as xy approach ab along any smooth curve. Well, by this I mean when you know that the limit exists and it is equal to L, then when limits go to that point on any smooth curve, it's going to be L as well. Well, smooth curve mean the curve that you can, the standard curve can be the line, can be the one that is not weird, the one is just the line one, the curve one, the parabola one, the x cube one, anything that is you can differentiate. So any curve that we are considering in this class, they are smooth, so it's fine. It just you can think of it as any curve. So remark one, what I want to say on remark one is if you know that limit exists, so it's gonna be limit is equal to L for any line that approach the point AB. Well, if you just use the contrapositive, by this I mean just reverse the sentence on number one. So you're gonna get here, if fxy has two different limits as xy go to ab, then limit of fxy xy go to ab here does not exist. Well, this is the way you can conclude that the limit does not exist. So if you can find two different limits, then you're done. Well, that means when you compute limit fxy when xy go to ab, so you can pick two different lines, and if you pick two different lines and then you compute limit and they give you something different, so your conclusion gonna be limit does not exist. Does it make sense? Because you have infinite number of paths that you can go to the point AB, right? Suppose the point that I am interested in is 0, 0 here, right? I can compute the limit when xy go to 0, 0 from this way. Suppose I compute limit xy go to 0, 0 from this way, and then I get limit equal to 1. And then I compute limit when xy go to this point, and I get limit equal to 0. Well, if you can find two lines that give you different limits, then you are done. Your conclusion gonna be limit does not exist. Well, because the theory said that if limit exists, it must be the same on every line, no matter how they approach 0, 0, but they're gonna give you the same limit. Well, to reverse that thing, if you see the two things that give you different limit, then you're done. You conclude that the limit does not exist. Well, we're gonna talk about this by using example. So coming up, you're gonna have two examples that I am going to show you about this technique. This technique is new. You have not seen it in Cal 1. So be attention on this thing. So let's look at, okay, before look at that example, so let's look at this thing. So this is the example that from the book. You can see that I have a function fxy here. and I have a function gxy here. You can see that if I want to compute the limit of fxy where xy go to 0, 0, you can see that when xy go to 0, 0 from of the function f, you can see that the point 0, 0 is here, the one that I have a red dot here. You can see that when xy approach 0, 0, the value just getting close to 1. So that means at the end, limit of fxy gonna be 1, because from any line, any approach, so you're gonna get 1. But if you look at the behavior of the g function, so if you have limit gxy, which is x squared minus y squared, x squared plus y squared here, you can see that if you come from the line x equal to 0 here, so it's always -1. And then when it approaches 0, 0, 0 here, the limit is -1. But if you come from the line y equal to 0 here, so the limit is 1. So that means you have two lines that if you approach from this way, you get limit equal to 1. If you approach from this way, limit equal to -1. So that will gonna be the conclusion that the limit does not exist on D and E. All right, let's do the real example. So this is the idea. Or let's do the real example, example 5. So let's go step by step together. So from the example 5, I want you to compute limit of this function where xy go to 0, 0. So we're gonna show that the limit does not exist. So on the exam or on the quiz or on the take-home quiz, everything, when the question asks you to show that the limit does not exist, you have to show your work in full steps. So that means you cannot skip steps. So my expectation, I want to see you pick two lines and then compute limit. So let's see how I do it. First of all, I am going to, let's think first. If you plug in number 0, 0, does it work? So you're gonna get 0 times 2, 0 plus 2 times 0, and then 0 minus 2 times 0. Well, it's gonna be 0, 0 over 0, okay. So I cannot conclude it by just plugging in. So this is not good. All right, next. Well, let's try, because the question said does not exist. So let's try to pick two different lines. So consider limit of this where xy go to 0, 0. So the first thing is that we know that the point 0, 0 is here. Well, you can pick any line that approach 0, 0. Well, the standard one is you pick the one that is easy to compute. So the first one I'm gonna pick, let's say x equal to 0 first, this line. Well, let's look at the behavior of limit by using the line x equal to 0. So the notation I'm gonna say on x equal to 0. So just add one more line and say here on x equal to 0. So we know that, hey, with respect to this notation, I'm gonna compute limit with respect to x equal to 0. So by this, I mean, you can plug in number 0 here. Well, because you just pick the line x equal to 0. All right. And then after that, once you plug in x equal to 0, so you're gonna have just 2y over -2y, right? And then they cancel out, so you get -1. So you're gonna get that the limit of this function on x equal to 0, this is -1. Well, this is you pick the line x equal to 0. All right. So let's pick another one. Well, if you want to pick the fancy one, you can. If you want to pick, well, let's see. If I want to pick the fancy one, I can pick the line here. I'm going to pick y equal to x because I want the fancy one. Well, y equal to x also approach 0, 0, 0, right? So I can pick the line y equal to x, for example. Well, what I'm going to have is consider limit x plus 2y over x minus 2y. x, y go to 0, 0, but this time I say on y equal to x. If I pick on y equal to x here, so that means I can replace x and y by, I replace x by y or replace y by x. So I'm gonna get limit of, well, let's say y plus 2y over y minus 2y then. Okay, good. All right, and then now I have, you can see on the top I have 3y, right? This is going to group it up to 3y, and this is going to be negative y. Okay, they cancel out, so you're gonna get negative 3. Well, now your conclusion gonna be, because you already found out that the limit from two different curves, they give you different number. So the conclusion is gonna be, well, I'm gonna say star and double star, because star and double star, right? Because the limit on different line, they're not equal to each other. We conclude that the limit of the given problem here does not exist when x, y go to 0, 0. Well, you may have a question that, Ajahn, why did you pick x equal to 0 and y equal to x? As I told you, you can pick any line you want. If you want the easy one, you can pick x equal to 0. You can pick y equal to 0. Well, that's the simple one people usually do, because x equal to 0 is easy, y equal to 0 is easy, y equal to x is easy. If you want to show your skill, you can pick something harder than me. You can pick y equal to x squared or something. You can pick y equal to x cubed or whatever. But as long as you pick the line that pass the point 0, 0, I mean approach the origin 0, 0, you will be fine. Does it make sense? Any line that approach 0, 0, you are good. But you have to find two different lines that give you two different limits. If you keep doing this way and you get the same limit all the time, that means maybe the limit exists, right? Because in case of the existence of limit, you're gonna get the same limit on every line. Does it make sense? All right. I will do one more example. Let's see. I think one more example, and then we can do two more slides, and then we can give you a break. All right. So let's do example 6. Well, this is the same difficulty of the exam and the quiz. So this is, well, supposed to be this kind of difficulty. So if you feel like, hey, you are comfortable with the content, well, that is good. That is good. All right. So example 6. So I want you to show that the limit of this thing does not exist. So let's do one more example. All right. What should we do? All right. Of course, because the question says limit does not exist, so we're gonna use the way that we're gonna pick two lines. So let's pick one thing. Let's pick the easy one. X equal to 0. It work. Okay, let's pick x equal to 0. Well, keep in mind that you can pick any line that approach 0, 0, right? So I'm gonna pick x equal to 0. All right. So what is going on here? Let's see. On x equal to 0, x squared over y. Well, I love to copy the question first all the time. I'm crazy, so I don't want to skip steps. So this is just plug in the number 0. So 0 square y over 0 to the 4th power plus y squared. So you can see that if I pick the line x equal to 0, the thing is that on the top one, you're going to have 0 squared times y, which is give you this 0. And on the denominator, you get 0 square, 0 to the 4th power plus y squared, which give you y squared. And then once you calculate that thing, so you're going to get 0 completely, right? Because the function is 0, right? Because just 0 over something that is non-zero, so you get just 0. Well, good. Well, my goal is I am trying to find another one that give me different limits. So let's pick another one. So let's say I pick, well, let's start from the easy one, y equal to 0. Well, I am not sure if I pick the right one. Well, but let's compute first. Y equal to 0. Well, I'm trying to be more lively with you. So I'm trying to just pretend that I know nothing, and then I just trying to follow the rules here. Well, let's see if it works or not. Well, well, if you pick y equal to 0, what happened is x squared times 0 over x to the fourth power plus 0. Well, you can see the top one go to 0, right? Because this is just completely 0. The bottom one is x to the fourth power 0 over x to the fourth. It's still 0, right? So this line, not good. Not good. Well, we're not going to use this line. Well, let's try something else. Well, this is not good, right? Okay, let's do the y equal to x. Spice it up a little bit. Y equal to x. So you can see y equal to x, y equal to x. Well, what if y equal to x? So it's going to be x squared times x here, because I can replace y and x, you know, same back and forth. So this is x to the fourth and then plus x squared. Interesting, because on the top, you're going to get limit x cubed. On the bottom, you get x to the fourth plus x squared. Does it work? So let's try to compute it. If I pull out x squared from the bottom, so I'm going to have x squared plus 1 here, and then on the top, I have x squared times x here, right? Well, the reason is just I am trying to cancel out x squared. I pull out x squared because, well, at the end, you're going to have limit x, y go to 0, 0, right? X over x squared plus 1, which is going to give you 0 over 0 squared plus 1, which is 0 again. Well, this line does not work again. So what else? So type in the chat, please. What line do you think that it would work? Well, about 25 students here. Well, give me an opinion. What should I pick to fix this question? Can it be the curve? Natsuki said yes. It can be anything, but that line just need to approach 0, 0, the origin 0, 0. All right, Nida, give us y equal to x squared. All right, so let's try y equal to x squared and see if it works. Well, you can see that what Nida said is y equal to x squared, which is good because y equal to x squared. Well, when you think that, should we use y equal to x squared? So first of all, you can see that y equal to x squared. This is a graph that approaches 0, 0, right? Because if you draw y equal to x squared, it's gonna be just that, blah, blah, blah. So anyway, it's, well, any line that pass 0, 0, that would be good to use. So you can use this thing, all right? Y equal to x squared, y equal to x squared, and let's see. Well, it looks good to me because, well, you have y equal to x squared, right? So the denominator, it looks good now because you can just build it up. So the power on the denominator, they are equal to each other now. So on the top, you're gonna have limit x to the fourth power over x to the fourth plus x to the fourth. Wow, this looks amazing. X, y equal to 0, 0, and then on y equal to x squared here. Okay, I need to, well, you cannot read my handwriting now, so I just make more space here. So x to the fourth. All right, and then you can see that the top one is x to the fourth, the bottom one is x to the fourth plus x to the fourth. So this is actually 1/2, right? Because x to the fourth gonna cancel out, so you get 1/2. Bang, this is good. So now our conclusion is going to be the limit. Okay. Because the limit from different curve are not equal to each other, we conclude that the limit does not exist. The limit x squared y over x to the fourth plus y squared here, xy approach 0, 0, does not exist. D and E. All right. So this is how we show limit does not exist. One thing to keep in mind is when you do the questions on the exam or on the homework, well, sometimes I'm going to say compute the limit. I didn't say that, show that it does not exist. So the first thing that you should do is you try to plug in number. And then if it does not work, you use the conjugate or factoring. If it does not work, if you feel like there's no way to factoring or conjugate, you can try to pick the line. If you keep picking the line and then you get the same number all the time, maybe the limit exists, but you just miss something. But if you pick like a few different lines and then you see the limit, that's the limit so different. So you find the pair that the limit are actually distinct. So that means the limit does not exist. Sounds good. All right, so we're gonna have about, I think, let's have a break, 5 to 7 minute break, and then we come back on. Oh well, it's just only 10:45. Well, let's do one more slide, and then we're gonna have a break. All right, so one more slide then. Sorry, it's too early to have a break, huh? Well, I will do one more slide. So when it hit 10:50, so I'm gonna have a break. All right, so well, we already know how to show that the limit does not exist, but you can see that one problem is sometimes you're gonna see the case that you keep picking the line and then you get limit equal to 0. It can be the case that when you have fxy here, right, and then you compute limit on x equal to 0, for example, you get limit equal to 0. You pick the line y equal to 0, you also get limit equal to 0. You pick the line y equal to x, limit is 0 again. The line y equal to x squared, limit equal to 0 again. It seems like you pick so many lines already, and then you always get 0, and you are about to give up. You feel like, hey, this is the end of the world. You cannot show that the limit does not exist. Well, this means maybe the limit is actually 0. So we're gonna have the theorem to show that if you, for some cases, you can show that the limit equal to 0. All right, so theorem. This is two-dimensional squeezing theorem. All right, let's see how it's work. So for two-dimensional squeezing theorem, they say that if you have f and g, they are functions of two variables. So you have f and g, the function of two variables, and you have two conditions. Number one, you know that the fxy here, when you take absolute value, it is bounded by a number m, where m greater than 0. So for some reason, you know that the function f is bounded by a number m. And number two, you also have the condition that the limit of gxy, where xy go to 0, 0, this is 0. If you have these two conditions, then you can conclude that the limit of fxy times gxy equal to 0, where xy go to 0, 0. Actually, it doesn't have to be 0, 0. It can go to any point A, B. But usually we're gonna work with 0, 0. All right. By this I mean, hey, this looks so abstract now, but it will get better in the next hour when we do the examples. Before the break, let me show you the idea. So the idea of this theorem is when you have fxy absolute less than or equal to m. So that means fxy is in between negative m and m, right? Because this fxy absolute less than or equal to m, you can expand it as this thing. And then you can see that if you multiply fxy and gxy together, so you multiply gxy to the inequality here, right? And then, well, if you want to compute limit of this thing, what is the limit? What is the limit of this thing? If you want to compute that, well, if you know that the limit of mgxy is 0 and limit of negative mgxy is 0, which you know because you're going to have another condition that limit g equal to 0. So this thing gonna give you 0 here, going to give you 0 here. M doesn't matter, it's just constant. So the limit on the top squeeze and the bottom squeeze, they are both 0. So it's going to force you that the limit fxy, gxy multiply together going to be 0 as well. Well, it looks abstract, but it's so helpful when you do the examples. So you can see the idea is similar to squeezing theorem in 1 dimension, but we just extend it into 2 dimensions. So on the next hour, we're going to come back and look how to manipulate this theorem into some examples. Sounds good? All right, if you have any question, let me know in the chat. So I'll give you a break now. So come back at, let's say 10:58, right? Okay, just 7 minutes. That should be good. 10:58, we come back and then we're gonna learn a few more and then we're done today. Good. All right. Okay, let's do 7-minute break. Let's look at example 7 here, which is we are going to look at how to apply two-dimensional squeezing theorem into examples. So again, we have two functions f and g. Well, what you need is you need the function f that is bounded by m, and you need the function g that is limit equal to 0. If you have these two conditions that I highlight in yellow and I highlight in light blue, you can multiply each other and then the limit of the product of f and g gonna be just 0. All right, let's look at how to do it. Example 7. So I'm gonna show you how to do that here by wait a second. I think I have a question in the chat. Someone just okay. Nachakiet said that is it necessary that bounded by m at AB? So when we say the function is bounded, it just, you know, it's when we say it's bounded, it's just bounded everywhere in, you know, it is not AB. It is not on the point AB. When they say the function is bounded here, bounded by m, it means in general on its domain of fxy, it must be bounded by m. It not just the point 0 AB. The point A bounded at the point AB is not enough. You need the whole domain. Well, at least you need the point near 0, 0. But well, the theorem that we're going to apply, we're going to use for the whole domain. So you will see in the example. So, well, let's do example 7 first, and then I will come back with your question. Okay, example 7. So we have we have to compute this limit. So I'm going to show you if I am a student, if I am a beginner, what I should do first is I am trying to plug in number 0 here. Well, this is the first thing that you should do all the time, because you know, you never know, sometimes you just plug in number and then you get something is not 0 over 0, and then you are done immediately. So fine. Here you're gonna say, hey, Ajahn, I get 0 over 0. So this is no good. So you still need to use something. And then you look at this question, I have no way to factoring because I have x squared plus y squared, which is give me no clue how to factor. So I'm just saying that I'm not going to do it. Factoring is so hard. Conjugation is so hard as well because I don't know what to multiply. So maybe I'm gonna pick the line and show that the limit does not exist. So let's try to pick x equal to 0. If I pick x equal to 0, I'm gonna get 0 on the top, right? And I'm gonna get 0 over y squared at the bottom. Well, this is going to be the case that I pick y equal to x equal to 0, and that will give me the limit go to 0 completely. Well, I can pick y equal to 0, and then that would be 2 times x squared 0 cube over x squared plus 0 square, which I mean on the top is 0 again, so it's gonna go to 0 again. If I trying to pick x equal to y, so I try so many things, x squared plus x squared, and then 2x squared x cube, right? Because I pick x equal to y. So this is going to be, actually it's going to be 2x, right? Because x to the, oh no, 2x to the 5th power over x to x squared, which is x cubed. It's go to 0 as well as xy go to 0, 0. So you can see that if you pick the line, at some point you're gonna get tired because you keep getting 0, and then you feel like, hey, Ajahn, I want to give up. This is all 0. I cannot find two lines that give me different numbers. Well, what I said is maybe it is actually 0. Well, this theorem gonna help you because this theorem gonna show you that the limit is equal to 0. So what I'm gonna do here, I have to pick f and y. So we're gonna use squeezing theorem into dimension. We're gonna pick f and g. We have to pick f and g properly to use a theorem. The function f that I am going to pick, I need the one that if I take absolute value, it's gonna be less than some number. And the function g that I pick, I need the function g that when I pick the function g, I have the limit that is equal to 0. So the trick is here. Well, usually you're gonna pick the denominator here to f. So I'm gonna pick x squared plus y squared to the f. The reason is because, well, you'll see in a minute. And then on the top one, I am going to split x squared to f. And the rest, the remaining 2 and y cube, I'm going to put it in G. So you can see that I pick f to be x squared plus y squared, and then I pick G to be 2y cube. The reason why I pick f to be x squared plus x over x squared plus y squared, this is because when I do x squared over x squared plus y squared, I can find a boundary easily by saying that this is x squared over x squared plus y squared, right? It must be less than or equal to x squared plus y squared over x squared plus y squared. Because on the top here, on the left-hand side, you have just x squared. Well, on the left-hand side, you have x squared. On the right-hand side, you have x squared plus y squared, which is bigger. Well, I should say at least x squared on the right-hand side because, well, you add y squared and y squared is bigger than or equal to 0 for sure, right? So on the top one, when you compare it, you're gonna get this inequality, and that will cancel out to be 1, which means you already have that, hey, condition number 1, absolute fxy less than or equal to 1. This is the reason why I say that every time when you see the denominator here, you should put the denominator here into the f1 because you expect that you're gonna make a bound over there. And then you just pick the one on the top smartly. Well, if you don't want to pick x squared, you can pick y squared over x squared plus y squared. This works too. And then you give the rest to x squared y on G. Well, the solution is not unique. By this, I mean, you can do so many ways and solve the problem. It depends on you. What are you going to pick f and g? There's not just one solution. There are so many solutions. The one I pick is x squared over x squared plus y squared into f. And then for 2, for the condition number 2, I am going to pick function g to be 2y cubed, and this is 2 times 0 cubed, which is 0. So perfect, I get two conditions I want. So by two-dimensional squeezing theorem, two-dimensional, one second, two-dimensional squeezing theorem, the one that we just did on slide 19, well, we conclude that limit of f and g multiplied together, this is equal to 0. X, y go to 0, 0, which means limit of that thing, the one we want, this is equal to 0. Sounds good? Well, some of you are going to say that I have no clue how to pick f and g. Well, this is going to be your, you have to practice because this is based on experience. If you do more and more and more problem, so you're going to see that this is how we pick f and g. So this is your first day. Again, this is your first day of learning limits in two dimension. So sometimes it is hard for sure on the first day, but once you practice again and again, you know, get more experience and can do it faster and faster. So I have a question for in the chat from Slataya. She asked us that why the first one is equal to 1. So again, let's look at this thing. So look at the laser one here. This is equal to 1 because I cancel out x squared and y squared. So this is 1. Okay, so I cancel out x squared and y squared. So it's get 1. Okay. All right, so let's do one more example. Well, we're going to climb up to the hard one. So example 8. All right, I have limit of 3xy over square root 3x squared plus y squared. Well, I will give you, well, you know, if this is the exam, so you're gonna have to start from plug in 0, try to conjugate, try to factor, and then try to pick the line. Well, let's suppose that we already know that those way are incorrect. So if you pick the line, you're gonna always get 0, 0, 0, 0, 0 for sure. So let's focus on the theorem that we're gonna use. So we're gonna let f and y and g here. Well, as I told you before, you start thinking using this theorem, you should start from different method first, and then this should be you know, the last one to pick to use because it is not easy. All right, so we're gonna have, we need to pick f and g here. As I told you that the best trick is you put the thing that you have in the denominator on f. So I'm gonna pick square root 3x squared plus y squared on f. But on the top here, well, on the denominator, it is clear that you're gonna put it on f. But on the top one, so I need to be smart. Well, let's try to pick, let's say y. Let's say y, and then t equal to 3x. Well, I do not know. Well, now we're gonna compute the condition number 1, which is absolute fxy, and see if we can bound it. So it's gonna be absolute y over square root 3x squared plus y squared. Interesting, right? You can see that this is going to be absolute y over square root 3x squared plus y squared. I can get rid of the absolute in the denominator because this is always positive, right? Square root is always positive, but on the top, I still have square root y there. Not square root y, sorry, absolute y. And then by this absolute y gonna be square root y squared. Would you agree? Absolute gonna be square root y squared. And then after that, square root 3x squared plus y squared. All right, I didn't do anything. I just switch square root y to switch absolute y to square root y squared. All right, and then after that, how do I bound this thing? So again, we can use the same technique. Last time we said that x squared over x squared plus y squared less than x squared plus y squared over x squared plus y squared. Here we're going to do the same thing. We're going to say, hey, why don't we just add 3x squared here? Which is okay, right? Because if you compare it, y squared always less than y squared plus 3x squared for sure. Always, right? Because 3x squared going to be bigger than 0. Or 3x squared going to be greater than or equal to 0. Well, that means you can have this relationship, and then on the denominator you have 3x squared plus y squared. And then the reason why I do this because I want to see the same thing so I can cancel out at the end. This is 1. Well, this line, this thing, this is not easy. Man, this is not easy. Well, you see me doing it like so quick and just simple because I did it so many times. Well, I probably did that like more than 100 times. But this is you are a student now. This is your first day. Well, take your time to understand this line because this is not easy. Well, when you do the problem by yourself, you're gonna spend a few more minutes on this line, which is fine, totally fine. Just go slow and try to absorb technique. All right. So some of you are gonna say, Ajahn, what if I do something different compared to you? Fine. So you can pick x as well. You can pick x over square root 3x squared plus y squared as well. It is also correct, but you just need to bow it properly. If you are not sure, just let me know. Send me an email or something. Can I do this or something? I will check it for you. And then now we have part 2. So limit gx y. So the part 2 is easy, right? The hardest one going to be the part 1 that you bow the function f. But for part 2, well, the remaining work is just simple because what you have left is just here, 3 times 0, which is 0. So by 1 and 2, we conclude that limit of this thing is equal to 0. This is actually by squeezing theorem into dimension. All right. Usually this is going to be the hardest content for limit and continuity. Well, last year I taught calculus 2, and this content seems to be the hardest one for student for this for this limit and continuity chapter. All right, so take your time to do that. So to understand that, well, at the end of this slide, I have practice problem for you, so you can do that exercise. All right. Well, now it's 11:15. I will spend half an hour more talking about continuity, and then we're gonna stop the class. So, any questions so far? Who opened the microphone? You have a question, Gan? No. Well, you can ask. Well, I'm happy to get questions. How do you know what to add in step 1? Okay. I have a question from student named Ru, right? ROO, Ru. He asked us that, he or she, I'm sorry, I cannot tell, but how do you know when to add, what to add in step 1? So this step 1 here again. So I am going to use the laser here. You can see that I add 3x squared here because I want to cancel out with my denominator. So, well, if you do y squared less than y squared plus x squared, that would be correct too. But at the end, you're going to get square root y squared plus x squared over square root 3x squared plus y squared. It is still not cancel out, right? Because they're not the same. They're not the same here. So why would I do that then? So I should do 3 here too as well, because if I have 3 here, the pattern gonna be the same, and then you can cancel out. Okay, all right. So I take more questions. So I have question from Nida. Where can we get the answer for the practice problem? Okay, I will chat about that thing after in the last 10 minutes. So just I will come back to that question, Nida. All right. Hope everyone is so far so good now. So not to get, you should I think I answered your question already. So you can see that when we bound fxy, we bound it on the whole domain. We didn't bound it on the point xy. All right. Well, let's talk about continuous function in two dimension a little bit, and then we're gonna look at practice problem together. All right. Well, let's move to the concept of continuity. This is the concept that is just, not that hard compared to limit. So this is what you did in Cal 1 in one dimension. When you say that limit, when you say the function is continuous as the point A, in one dimension, you say limit must exist, right? And then you mean the point f, the function f at A exists, and then limit exists, and then they are equal to each other. That means the function f is continuous at the point A. This is in one dimension. So we're gonna copy the idea, copy and paste it in two dimension. So in two dimension, this is what we have. You're gonna say that fxy is continuous in two dimension at the point AB. Well, if you have three conditions as well. So the condition number one, well, for sure, f must be exist. So before you use f at the point A, at A, now you use f at the point AB. You just extend it into two dimension. And then number two, limit fxy, xy go to AB, exists. You see that? So you need to compute limit as well, because you need number two, that limit exists. And then number three, if number one and number two equal to each other, then you say the function is continuous. All right. So again, this is the same idea with Cal 1, but you just extend everything into two dimension. That is how we check the continuous function or check the continuity at the point AB. We have something better than that, because polynomials, trigonometric function, logarithmic function, exponential function, everything, they are all continuous. And you also know that the sum of the continuous function is also the continuous function. The product of the continuous function is also the continuous function. The quotient of the continuous function is also continuous function wherever the denominator is not equal to 0. So everything you know from Cal 1, you can use it. Polynomial always continuous. Trigonometric always continuous. Log is always continuous. So that include almost every function you know, right? So that's fine. So those functions, they are easy because you can assume the continuity of those functions. All right, so let's see, we have how many examples? We have 3 examples here. Well, I think we're gonna spend about 7 to 8 minutes on each question, and that will be the end of the lecture. And we're gonna talk about practice problem. So let's do it together. Example 9. All right, example 9 here. So again, the question 9 say that we want to show that the function here is continuous at the point 0, 0. So in order to show that the function is continuous at 0, 0, first you need to compute f at AB, right? AB here is 0, 0. So I am going to compute f 0, 0. By looking at the function here, f 0, 0 is 0 because you use the second step function here. So number 2, you need limit fxy, xy go to 0, 0. Here we go. This is not easy, right? Because you need limit xy go to 0, 0, and then you have 5xy squared over square root x squared plus y squared. All right. Well, you can see that we have to go back to squeezing theorem to solve this thing, right? Well, you can try pick the line. If you pick the line, you can pick x equal to 0, y equal to 0, and so on. And well, you still get 0, 0, 0, 0. But the best way to solve this thing, so I'm gonna do in the box here. So I'm gonna let f x y to be I have square root x squared plus square here, and then I'm gonna pick gxy to be something that we have left. So let's trying to bound f first. So, well, you have seen the technique already. So if I want to bound this, so I can pick, let's say I pick just one x here. If I pick one x here, so it's gonna be x here gonna be equal to square root x square, right? Over square root x square plus y square. And then you can see that you can bound it by, because the denominator you have x square plus y square, the top one you would need the same thing because you want to cancel out and then you get 1 at the end. So on the top one, so I'm gonna add y square here because you say that, hey, it works because x square less than x square plus y square, and then they cancel out perfectly, so you get 1. So this should work. So good, f, and then g gonna be the remaining thing that you don't put it in f. So this is going to be a 5y square. And then, well, from here you conclude that, hey, limit f and g equal to 0. Wow, this is so good. Well, I skip one step, but you need to say that limit gx y equal to 0 as well. But from that, so you say that limit f top g is equal to 0, which means you're gonna get number 2, the condition of continuity, you get 0 as well. And then number 3, because 1 and 2 are equal to each other, well, number 3, you can say just 1. We have number 1, which is f00, right? Equal to number 2, which is limit xy go to 0, 0 of fxy. All right, they are equal to each other because they are all 0. So to sum up, you have f is continuous, right, at 0, 0. You can see that to check the continuous function at the point, it is not hard. I mean, the concept is not hard. The hard part is going to be, you need to compute limit inside there. So that's going to give you a hard time to compute limit inside the continuity check. Does it make sense? All right. I am going to speed it up a little bit because we don't have much time left, only half hour left. We have 2 examples and also practice problem. So let's look at examples 10 and 11. So if I go too fast, let me know in the chat so I can slow down. So let's look at example 10 here. What we have is, we have the function here. All right, we wanna look at the continuity of this function. They didn't say about the point that we want to check, but you can see that if the point AB is not equal to 0, 0, well, if the point AB is not equal to 0, 0, then the function f is continuous at AB, right? Well, you can see that the point that you're going to have a problem is 0, 0, because if the function is, if the point AB is not equal to 0, 0, you're going to use the same function all the time because you're going to use the first condition, and then, you use the same function all the time, which is, the function is continuous at any point at x, at AB equal to 1, 1, at AB equal to 1, 2, at AB equal to negative 1, 1. Any point AB that is not equal to 0, 0, well, there's no point to talk about continuous check because you use the same function all the time, and yes, for sure it is going to be continuous. So the only point that you need to be careful is when AB equal to 0, 0. We need to check the continuity at 0, 0. Okay, good. So let's do it. First of all, I'm gonna do the same thing. F0, 0. This is 0. Good. And then number 2. All right. So we need to compute limit y to the 10 minus 2x squared over y to the 10 plus x squared. x, y go to 0, 0. All right, how do I compute this thing? So first of all, I'm trying to plug 0 in. So 0 to the 10 minus 2, 0 square, and then 0 to the 10 plus 0 square, 0 over 0, right? So no good for just plugging in. Can we factor out? You can see that this is not a good idea to factor, right? Because y to the 10 plus x squared, I'm not trying to factor for sure. This is terrible to factor. Well, what if we pick the line? All right, let's say, what if I pick x equal to 0? What happened? If I pick x equal to 0, I have y to the 10 minus 2 times 0, and then y to the 10 plus 0 square. That is 1. The limit is going to go to 1. What if I pick y equal to 0? Well, let's try the simple one. So again, you can pick any line that approach the point 0, 0, right? Because you are computing the limit when x, y go to 0, 0. Here gonna be 0 to the 10 minus 2 x squared over 0 to the 10 plus 2 plus x squared. Looks good, right? It doesn't look like you gonna have a hard time to pick the line, because here you get -2, right? It's gonna approach -2. Am I right? Am I right, everyone? Right? Do you agree with me? You just pick the line, any line you want. Yeah. So that means you don't have to go to squeezing theorem at all. So you already found that, yeah, we have two lines that the limit, they are not equal to each other. So what you're gonna do is you're gonna say, hey, from here, consider limit x, y go to 0, 0. Okay, let's say on x equal to 0 first. I have that. Well, I'm sorry, I am so addicted to copy the question, so I have to write everything in full. So it's gonna take time for me to write everything. So here, y to the 10 minus 2 times 0 square over y to the 10 plus 0 square. So, well, you can see this is 1. And then you can find another line that, let's say this line, I'm gonna pick y equal to 0, because, okay, copy question first. Copy the question first. And then I plug in y equal to 0 here. Well, here, if you want to pick different line compared to me, it's also good too. I mean, some of you are going to pick y equal to x to the 5th power or something like that. Totally fine. Because any line that gives you different limit would work. So this is going to be -2, because I cancel out that thing. So I have 1 and -2, which they are not equal, right? Which means the limit here does not exist. Does not exist, right? Does not exist because of this thing. That means, to sum up, f is not continuous. Well, because the condition number 2 does not work out. So that means f is not continuous at 0, 0. So for this function, f is continuous on any point except 0, 0. Sounds good? And this is the minimum that, I mean, if I ask you on the exam or on the quiz, you should write it as like this, as minimum. So if you skip steps, well, you lose the point. So the minimum, you should at least do minimum as my slide. That is my expectation. Otherwise, no, I will not give you full credit if you just skip step. Sounds good? Let me see the chat first, if we have any question more. Okay, not yet. Okay, we're gonna move to the last example for today. And then after that, we're gonna talk about practice problem a little bit, so you can get something to practice. Okay, good. We have example 11, the last one for today. All right, good timing. All right, Well, let's do one more question on continuity. So this question is a little bit different from the previous one because they ask you to find the value of the constant k such that the function f is continuous. So that means you already know that the function is continuous, but you just need to find the value of k. Well, when they say f is continuous on the domain R squared here, that means f is continuous everywhere, right? That means f is continuous at 0, 0, 2. So we're going to use that thing to help us to find k. Well, note that we know that f is continuous at xy equal to 0, 0. Well, we know that. We know that because f is continuous everywhere. The question say everywhere in R squared. Now, because f is continuous at 0, 0, so we have f0, 0 exists, right? Well, f0, 0 is equal to k in this question. Good. And then number 2, limit of fxy, where xy go to 0, 0. Well, this must exist and also equal to k as well, right? Well, because in order to hold the continuity property, you need 1 equal to 2. So that means you have that 1, f0, 0 equal to k. You have limit here and 1 equal to 2. That means k can be computed by using limit, right? Well, if you can compute limit of xy go to 0, 0, that is just k, right? Because you need number 2 here equal to number 1 here. So they must be equal to each other in order to hold the continuity property. So actually k equal to limit of fxy where xy go to 0, 0. Well, so the remaining of your work is just compute the limit. All right, so let's look at the limit. This limit is not easy. So x squared times sine xy over x squared plus y squared. Xy go to 0, 0. All right, what should we do? So first of all, I'm going to do the same thing as before. So I'm going to just trying to plug in number 0. Of course, I get 0 over 0. No good. And then now I can, what else I can do? I can, well, factoring is not a good way to do, right? Because you have sine xy on the top. So, well, when you see trigonometric function, you do not want to factor or something. It's going to be terrible or conjugate. So, well, let's pick the line then. So what if I pick x equal to 0? I get 0 on the top. And then 0 square plus y square at the bottom, which is 0, right? This is, I pick x equal to 0. If I pick y equal to 0, what do I get? X squared times sine 0, which is 0 as well. And then x squared plus 0 square, which is actually go to 0 as well. This go to 0 as well. What if I pick y equal to x? X squared sine x squared, and then over x squared plus x squared, right? Here you're gonna get 1/2 times sine x squared, which is go to 0 as well. It's go to 0 as well because x go to 0. Well, after you pick these 3 curves, you can see that completely go to 0. And then if you try keep picking another different line, you still get 0 for sure, right? Because the behavior of this thing is kind of clear to me that, well, you're gonna get, if you keep picking the line, you cannot avoid sine xy here, and sine xy here gonna dominate the thing on the top, and you're gonna get the limit equal to 0 all the time, which means, well, we give up on picking the line then. So we're gonna do two-dimensional squeezing theorem. So we're gonna let f and y to be something that we can bound, and then we can just compute the limit there. So we're gonna let f to be, okay, because of that, I'm gonna do x squared plus y squared to f. And then what I want, if I want fxy to be bounded by something, well, which at the end, what I want, you have seen it so many times. What I want at the end, if I get x squared plus y squared on the top as well, I can say this is 1. If I can bound that, it's going to be perfect. So what should I pick to f here? So you can see, luckily, you have x squared plus y squared here. Follow the one that I highlight in orange, x squared plus y squared here. And then you have x squared here. That's why I say pick x squared here is the best one, because you're going to have x squared here. And then you can just do the inequality here, which is good, right? And then you pick the remaining term of what you do not want into gxy, and you hope that limit of g gonna give you 0 as well, which is 0, right? Because this is psi 0, which is 0. Well, from 1 and 2, you can compute limit by using two-dimensional squeezing theorem. You're gonna have limit of the one you want, x squared psi xy over x squared plus y squared. This is 0. And this is actually k equal to 0. That will give you the continuous on the entire domain. Sounds good? All right, so that is what we learned today. We learned how to compute limit in 2 dimensions, and we learned how to check the continuous function, the continuous property in 2 dimensions. So hopefully it is not that hard for you. So at the end of each topic, I give you practice problem. So this is similar to what I'm going to ask on the exam or take-home quiz. So if you do it and you complete it all, for example, if you can do it all here without any trouble, you should be good on the exam, because the exam is not going to be harder than this for sure. Well, usually what I usually do is I will let you do practice problem for a while, and then I will give the solution via my YouTube channel. If you want to check the solution after, you can go to my YouTube channel and you find the clip that I show you solution to practice problems. And then I'm going to show you step by step how to do each question on that clip. So but do it first, because don't wait until I upload my solution, because I'm going to delay about 2 weeks to upload my solution for practice problem, because I want to let you do that first. So do that as many as you can. Example 12, 13, 14, 15, 16, 17. Well, and 2 weeks after, we'll check the solution with my YouTube channel. Does it make sense? So you can check what you did is right or wrong. Well, you can see that, hey, here, this is the easy question. So, well, you can see this is conjugate question, right? This is the limit does not exist. So maybe you pick the line. Well, everything is just similar to the lecture today, right? Here you check the continuous thing. So maybe you pick the line, or you use the technique that the squeezing theorem. And here you just need a squeezing theorem for sure. Yeah, this is similar to what we just did, or something like that. So let's try to do practice problem by yourself first, and then check with my solution after. Okay, sounds good. All right, anything else? Any questions? All right. Any question in general? So next week we're gonna start partial derivative. So next week we're gonna see how to extend differentiation into 2 dimensions. Well, differentiation is going to be longer compared to limit, because you see the problem, right? Because differentiation, we have two variables now, x and y. So it is not easy. We're gonna define how to differentiate with respect to x and how to differentiate with respect to y, and we're gonna look at the application of differentiation to find the maximum and minimum of three-dimensional things, well, which is a little bit harder compared to limit and continuity. So that is what are we going to discuss next week. So, but for this week, I hope you enjoy the lecture, and thank you everyone for attending. All right, if you don't have any questions, so you can go. Thank you everyone. Sounds good. All right. 11:45. So I'm gonna end the lecture now. All right, thank you.